In mathematical logic, the Peano axioms, also known as the Dedekind Peano axioms or the Peano postulates, are a set of axioms for the natural numbers presented by the 19th-century Italian mathematician Giuseppe Peano. These axioms have been used nearly unchanged in a number of metamathematical investigations, including research into fundamental questions of whether number theory is consistent and complete. The need to formalize arithmetic was not well appreciated until the work of Hermann Grassmann, who showed in the 1860s that many facts in arithmetic could be derived from more basic facts about the successor operation in induction. In 1881, Charles Sanders Peirce provided an axiomatization of natural number arithmetic. In 1888, Richard Dedekind proposed another axiomatization of natural number arithmetic, and in 1889, Peano published a more precisely formulated version of them as a collection of axioms in his book, The Principles of Arithmetic Presented by a New Method. The Peano axioms contain three types of statements. The first axiom asserts the existence of at least one member of the set of natural numbers. The next four are general statements about equality. In modern treatments, these are often not taken as part of the Peano axioms, but rather as axioms of the underlying logic. The next three axioms are first-order statements about natural numbers expressing the fundamental properties of the successor operation. The ninth, final axiom is a second-order statement of the principle of mathematical induction over the natural numbers. A weaker first-order system called Peano arithmetic is obtained by explicitly adding the addition and multiplication operation symbols and replacing the second-order induction axiom with a first-order axiom schema formulation. When Peano formulated his axioms, the language of mathematical logic was in its infancy. The system of logical notation he created to present the axioms did not prove to be popular, although it was the genesis of the modern notation for set membership and implication. Peano maintained a clear distinction between mathematical and logical symbols, which was not yet common in mathematics. Such a separation had first been introduced in the Begriffsschrift by Gottlob Frege, published in 1879. Peano was unaware of Frege's work and independently recreated his logical apparatus based on the work of Boole and Schroeder. The Peano axioms define the arithmetical properties of natural numbers, usually represented as a set n, or the signature for the axioms includes a constant symbol 0 and a unary function symbol s. The constant 0 is assumed to be a natural number. 0 is a natural number. The next four axioms describe the equality relation. Since they are logically valid in first-order logic with equality, they are not considered to be part of the Peano axioms in modern treatments. For every natural number x equals x, that is, equality is reflexive. For all natural numbers x and y, if x equals y, then y equals x, that is, equality is symmetric. For all natural numbers x, y and z, if x equals y and y equals z, then x equals z, that is, equality is transitive. For all a and b, if b is a natural number and a equals b, then a is also a natural number, that is, the natural numbers are closed under equality. The remaining axioms define the arithmetical properties of the natural numbers. The naturals are assumed to be closed under a single-valued successor function s. For every natural number n, s is a natural number. Peano's original formulation of the axioms used 1 instead of 0 as the first natural number. This choice is arbitrary, as axiom 1 does not endow the constant 0 with any additional properties. However, because 0 is the additive identity in arithmetic, most modern formulations of the Peano axioms start from 0. Axioms 1 and 6 define a unary representation of the natural numbers. The number 1 can be defined as s, 2 as s, and, in general, any natural number n is the result of n-fold application of s to 0, denoted as Sn. The next two axioms define the properties of this representation. For all natural numbers m and n, m equals n if and only if s equals s. That is, s is an injection. For every natural number n, s equals 0 is false. That is, there is no natural number whose successor is 0. Axioms 1, 6, 7, and 8 imply that the set of natural numbers contains the distinct elements 0, s, s, and furthermore that 0, s, s, n. This shows that the set of natural numbers is infinite. However, to show that n equals 0, s, s, it must be shown that n, 0, s, s, i.e., it must be shown that every natural number is included in 0, s, s. To do this, however, requires an additional axiom, which is sometimes called the axiom of induction. This axiom provides a method for reasoning about the set of all natural numbers. If K is a set such that 0 is in K, and for every natural number n, if n is in K, then s is in K, then K contains every natural number. The induction axiom is sometimes stated in the following form: if phi is a unary predicate such that phi is true, and for every natural number n, if phi is true, then phi is true, then phi is true for every natural number n. In Peano's original formulation, the induction axiom is a second-order axiom. It is now common to replace this second-order principle with a weaker first-order induction scheme. There are important differences between the second-order and first-order formulations, as discussed in the section models below. Arithmetic. The Peano axioms can be augmented with the operations of addition and multiplication and the usual total ordering on n. The respective functions and relations are constructed in second-order logic, and are shown to be unique using the Peano axioms. Addition is a function that maps two natural numbers to another one. It is defined recursively as, for example, a plus 1 equals a plus s equals s equals s. The structure is a commutative semi-group with identity element 0, is also a cancellative magma, and thus embeddable in a group. The smallest group embedding n is the integers. Multiplication. Similarly, multiplication is a function mapping two natural numbers to another one. Given addition, it is defined recursively as, it is easy to see that setting b equal to 0 yields the multiplicative identity. A 1 equals a s equals a plus 0 equals a. Moreover, multiplication distributes over addition. A equals plus, thus, is a commutative semi-ring. Inequalities. The usual total order relation on natural numbers can be defined as follows, assuming 0 is a natural number. For all a, b, n, a, b if and only if there exists some cn such that a plus c equals b. This relation is stable under addition and multiplication. For, if a b, then a plus cb plus c, and a cbc. Thus, the structure is an ordered semi-ring, because there is no natural number between 0 and 1, it is a discrete ordered semi-ring. The axiom of induction is sometimes stated in the following strong form, making use of the order. For any predicate phi, if phi is true, and for every n, kn, if kn implies phi is true, then phi is true. Then for every nn, phi is true. This form of the induction axiom is a simple consequence of the standard formulation, but is often better suited for reasoning about the order. For example, to show that the naturals are well-ordered, every non-empty subset of n has a least element, one can reason as follows. Let a non-empty xn be given and assume x has no least element. Because 0 is the least element of n, it must be that 0x. For any nn, suppose for every kn, kx, then sx, for otherwise it would be the least element of x. Thus, by the strong induction principle, for every nn, nx. Thus, xn equals, which contradicts x being a non-empty subset of n. Thus x has a least element. First-order theory of arithmetic. All of the Peano axioms except the ninth axiom are statements in first-order logic. The arithmetical operations of addition and multiplication and the order relation can also be defined using first-order axioms. Such a schema includes one axiom per predicate definable in the first-order language of Peano arithmetic, making it weaker than the second-order axiom. First-order axiomatizations of Peano arithmetic have an important limitation, however. In second-order logic, it is possible to define the addition and multiplication operations from the successor operation, but this cannot be done in the more restrictive setting of first-order logic. Therefore, the addition and multiplication operations are directly included in the signature of Peano arithmetic, and axioms are included that relate the three operations to each other. The following list of axioms, which contains 6 of the 7 axioms of Robinson arithmetic, is sufficient for this purpose. Xn 0s x, yn, s equals s, x equals y, xn, x plus 0 equals x, x, yn, x plus s equals s, xn, x0 equals 0, x, yn, xs equals xy plus x. In addition to this list of numerical axioms, Peano arithmetic contains the induction schema, which consists of a countably infinite set of axioms. The first-order induction schema includes every instance of the first-order induction axiom, that is, it includes the induction axiom for every formula phi. Equivalent axiomatizations. There are many different, but equivalent, axiomatizations of Peano arithmetic. While some axiomatizations, such as the one just described, use a signature that only has symbols for 0 and the successor, addition, and multiplications operations, other axiomatizations use the language of ordered semirings, including an additional order relation symbol. One such axiomatization begins with the following axioms that describe a discrete ordered semiring, i.e., addition is associative, i.e., addition is commutative, i.e., multiplication is associative, i.e., multiplication is commutative, i.e., the distributive law, i.e., 0 is the identity element for addition, i.e., 1 is the identity element for multiplication, i.e., the less than operator is transitive, i.e., the less than operator is irreflexive. The theory defined by these axioms is known as par minus. Par is obtained by adding the first-order induction schema. An important property of par minus is that any structure or M satisfying this theory has an initial segment isomorphic to n. Elements of M n are known as non-standard elements. Models. A model of the Peano axioms is a triple, where n is a set, 0 n and s. Nn satisfies the axioms above. Dedekind proved in his 1888 book, What are Numbers and What Should They Be, that any two models of the Peano axioms are isomorphic. In particular, given two models n of the Peano axioms, there is a unique homomorphism F, nar nb satisfying, and it is a bijection. This means that second-order Peano axioms are categorical. This is not the case with any first-order reformulation of the Peano axioms. However, non-standard models, although the usual natural numbers satisfy the axioms of par, there are other non-standard models as well. The Compactness Theorem implies that the existence of non-standard elements cannot be excluded in first-order logic. The Upward-Lowenheim-Skolem theorem shows that there are non-standard models of par of all infinite cardinalities. This is not the case for the original Peano axioms, which have only one model, up to isomorphism. This illustrates one way the first-order system par is weaker than the second-order Peano axioms. When interpreted as a proof within a first-order set theory, such as ZFC, Dedekind's categoricity proof for par shows that each model of set theory has a unique model of the Peano axioms, up to isomorphism, that embeds as an initial segment of all other models of par contained within that model of set theory. In the standard model of set theory, this smallest model of par is the standard model of par. However, in a non-standard model of set theory, it may be a non-standard model of par. This situation cannot be avoided with any first-order formalization of set theory. It is natural to ask whether a countable non-standard model can be explicitly constructed. The answer is affirmative, as Skolem in 1933 provided an explicit construction of such a non-standard model. On the other hand, Tenenbaum's theorem, proved in 1959, shows that there is no countable non-standard model of PAR in which either the addition or multiplication operation is computable. This result shows it is difficult to be completely explicit in describing the addition and multiplication operations of a countable non-standard model of PAR. However, there is only one possible order type of a countable non-standard model, letting omega be the order type of the natural numbers, z to be the order type of the integers, and a to be the order type of the rationals. The order type of any countable non-standard model of PAR is omega plus zeta eta, which can be visualized as a copy of the natural numbers followed by a dense linear ordering of copies of the integers. The standard construction of the naturals, due to John von Neumann, starts from a definition of 0 as the empty set, and an operator S on sets defined as S equals A. The set of natural numbers n is defined as the intersection of all sets closed under S that contain the empty set. Each natural number is equal to the set of natural numbers less than it, and so on. The set n together with 0 and the successor function S. Nn satisfies the Peano axioms. Peano arithmetic is equiconsistent with several weak systems of set theory. One such system is ZFC with the axiom of infinity replaced by its negation. Another such system consists of general set theory, augmented by an axiom schema stating that a property that holds for the empty set and holds of an adjunction whenever it holds of the adjunct must hold for all sets. Interpretation in category theory. The Peano axioms can also be understood using category theory. Let C be a category with terminal object 1C, and define the category of pointed unary systems, US1 as follows. The objects of US1 are triples where X is an object of C, and 0x, 1CX and SX. XX are C morphisms. Imorphism phi is a C-morphism phi. XY with phi 0x equals 0y and phi SX equals psi phi. Then C is said to satisfy the Dedekind Peano axioms if US1 has an initial object. This initial object is known as a natural number object in C. If is this initial object, and is any other object, then the unique map U is such that this is precisely the recursive definition of 0x and SX. Consistency. When the Peano axioms were first proposed, Bertrand Russell and others agreed that these axioms implicitly defined what we mean by natural number. Henry Poincaré was more cautious, saying they only defined natural numbers if they were consistent. If there is a proof that starts from just these axioms and derives a contradiction, such as 0 equals 1, then the axioms are inconsistent, and don't define anything. In 1900, David Hilbert posed the problem of proving their consistency using only finitistic methods as the second of his 23 problems. In 1931, Kurt Gödel proved his second incompleteness theorem, which shows that such a consistency proof cannot be formalized within Peano arithmetic itself. Although it is widely claimed that Gödel's theorem rules out the possibility of a finitistic consistency proof for Peano arithmetic, this depends on exactly what one means by a finitistic proof. Gödel himself pointed out the possibility of giving a finitistic consistency proof of Peano arithmetic or stronger systems by using finitistic methods that are not formalizable in Peano arithmetic. And in 1958, Gödel published a method for proving the consistency of arithmetic using type theory. In 1936, Gerhard Gentzen gave a proof of the consistency of Peano's axioms, using transfinite induction up to an ordinal called epsilon 0. Gentzen explained, "The aim of the present paper is to prove the consistency of elementary number theory, or, rather, to reduce the question of consistency to certain fundamental principles. Jensen's proof is arguably finitistic, since the transfinite ordinal epsilon 0 can be encoded in terms of finite objects. Whether or not Jensen's proof meets the requirements Hilbert envisioned is unclear. There is no generally accepted definition of exactly what is meant by a finitistic proof, and Hilbert himself never gave a precise definition. The vast majority of contemporary mathematicians believe that Peano's axioms are consistent, relying either on intuition or the acceptance of a consistency proof such as Jensen's proof. The small number of mathematicians who advocate ultrafinitism reject Peano's axioms because the axioms require an infinite set of natural numbers.